We're going to use a process called Gauss-Jordan method to solve some systems of linear equations today. And this process is going to involve writing our system of equations as an augmented matrix. So an augmented matrix is a matrix that represents a system of equations. You have columns that represent the coefficients on each variable, and then one for your constants. So if I'm going to represent my first equation here, I'll have my coefficients in 3 columns, and then my constants separated by that vertical bar, which has a name, and I can never remember it. But my third equation, be careful that there's 0 y's in there, so make sure you put 0 in for your coefficient on your y column. And that is a 3x4 augmented matrix. If you look at the second example, we're going to turn it back into the equations that it represents. So first row says that we have 1x plus 0y plus 0z equals 2, or just x equals 2. My middle row corresponds to y equals -4, and my bottom row to z equals 5. So Gauss-Jordan elimination is a bit of a longish process. It's very easy to program computer systems to do, so that's kind of why this algorithm was developed for solving systems of equations. How it goes is our goal is to get a system of equations in the form that we had in the previous example, where you can directly see your values of your variables. And if you are starting it off, you're going to want to write your system of equations as an augmented matrix. So I'm going to go ahead and do that first. And then the first step in our process is going to be to get 1 as our first element in column 1. So to get that to be a 1, it's easiest to remember that this still represents that top equation. And if you think about if you're solving and trying to get that to be a 1 instead of a 3x, you would divide the entire equation by 3 to get an equivalent equation where the coefficient on x is 1 instead. So I'm going to do the same thing on the top row in my matrix because it represents that equation. This is really just kind of a streamlined process, I guess. So if I divide that entire top row by 3, I get that new top row. It's a good idea to kind of label what's happening so people can follow your work. Notation-wise, you could write that as row 1 gets multiplied by 1/3. If you look at step 2, we want to get the rest of column 1 equal to 0. So where 2 is right now, we want there to be a 0. I just am going to think about, again, the equations that are being represented by my 2 rows in my matrix, and this is really just elimination. So if I was going to get to eliminate my x, I could multiply my top equation, my top row of my matrix, by -2, and then that would eliminate the +2 in my bottom row and give me a 0x, which is what I want. So that's what I'm going to do. I'm going to multiply my top row of my matrix by -2 and then add it to my bottom row to get my new bottom row in my matrix. So you're going to end up with a 0x -19/3 y and 0. And then I'm going to rewrite that matrix with my new coefficients. Notation-wise, some people will write, okay, I multiplied row 1 by -2. I added it to row 2, and then do a little arrow for I put it back in row 2. That should say 2, not 1. All right, so we're halfway done with our process. Now I want to go to column 2 and get my 1 in that column. You always want to get the 1s first along your diagonal when you're working in each column before you get your 0s. So first thing I'm going to do here is rewrite for my row 1 because I don't need to change anything in it. And then if you think about the equation that this represents, I could multiply by -3/19 or divide by -3/19 to get a 1 there instead. If I go back up to my equation and think about it, since all the rest of those values are 0, it's not going to really change anything except make that a 1 because multiplying 0 times -3/19 won't change it. Now I need where my 2/3 is at to be a 0 as well. Same idea as before, thinking about eliminating that. So if I want to eliminate that 2/3 y and get 0y there instead, I could multiply my second row in my matrix, or the second equation that it represents, by -2/3, and then add them together to get my new first row that has a 0. So I'm going to do that. Multiply by -2/3. It's going to give me new equivalent equation there. And then if I add those together, it is just going to give me 1x plus 0y equals -3. And that's my new top row. And that'll pretty much wrap up my Gauss-Jordan elimination. At least it's got it in our goal form that we were trying to get to, where you can see that the top row represents the equation x equals -3, and the bottom row represents the equation y equals 1. And if you're like, oh my goodness, why? Well, this method is very handy when you have large systems of equations because the procedure can be programmed into a computer. Is it overkill when it's just 2 variables? Probably, but I want you to see how the process goes. Let's look at another one, and I'm going to kind of not write out as many steps. So augmented matrix, you're gonna have to start by getting 1 in the upper left-hand corner by dividing that entire first row by 2. And then here's my result real quick. Now I want to get where my 4 is currently to be a 0, because I worked down my column and get everything else to be zeros. So what I'm going to do is multiply my top row by -4 and then add the top and bottom row together, because that would give me 0. So I'm just rewriting off to the side here my coefficients. If I multiply my top row by -4, I'll have -4, 8, and -12, and then I can add those together, and my value of 4x is eliminated, and now it is a 0x, which is what I wanted. So that's my new second row. Write it back. I didn't change my top row, I just kind of off to the side used a new version of it to get my new second row. Now I need my 1 in the lower right hand corner, and to get that 1 I can divide row 2 by 6 and then write my new row 2 down, 0, 3, and -6. Top row hasn't changed. Last thing I need is a 0 in column 2 in that top row there. So I'm going to multiply, I'm going to use the one that I got, my 1 in my second row. If I multiply it by a +2 and then add it together, it'll give me my new first row of 1, 0, and -1. So rewriting my bottom row because I did not change it, and then my new top row that I just got gives me that matrix, which allows me to see that x equals -1 and y equals -2. So let's talk special cases here. So I've gone through my Gauss-Jordan elimination process, and I've reached the point where my new second row after my previous operation is going to be all zeros. If you think about what that means in terms of the equation that it represents, it's telling you you have 0x plus 0y equals 0, or that 0 equals 0. Well, that means that really these two equations that I have are equivalent equations, and they're the same line. So any point that is a solution to the system of two equations is going to be, any point that is on one line is going to be on the other line, because they're really the same line. So to write my solution set, I don't need to go any further in my Gauss-Jordan elimination method. I can just say, okay, it's going to be all points that are on my line, or of the form, we'll use x as my arbitrary variable, and then I'll solve for y to get it in terms of x here. I'm going to use my second equation, that looks easier. So if I solve that one for y, that's going to give me 8y equals 6x plus 14. divide by 8, and you're going to get y equals 2/3 x plus 14 over 8 would be 7 over 4. So that would be my solution set to that system of equations. Any points that are of that form. So another special case I could have is if you reach the point where on the left side where your variables are represented, you have all zeros, and on the right side it's a constant. Then you have a statement that's not true because you have something that says 0 equals another non-zero number, which is not possible. So in that case, it would be no solution. It's important to recognize those cases when you come across them using Gauss-Jordan elimination, because it's not really possible to go further using our Gauss-Jordan elimination process, but we can still figure out our solution set or state that there is no solution.